In this example, we're going to practice with the idea of the sample variance being distributed with chi-squared of n minus 1 degrees of freedom. So this is exercise 5.5 in your textbook. So you've got a random sample of size 16 taken from a normal distribution with mean 50 and variance 100. And this problem asks you to compare a couple of different probabilities. The first one asks you for the probability that the sum of the squares of each x bar minus the 50, which is the population mean, the squares of those differences, sum that up from 1 to 16, is between those two numbers that you were given. Part B looks similar, but rather than doing the deviations from the population mean, you're doing the deviations from the distribution of the sample mean, so the x bar minus x bar squared. So let's compare how these two parts are different and yet similar. So for part A, remember that, just like we talked about before in the previous video, that if you have a standard normal distribution, then that square of that standard normal distribution is a chi-square on 1 degree of freedom. And then if you take the sum of independent chi-squared random variables, you still get a chi-squared and you add the degrees of freedom. So if we look at that inside of that part A, where we had the x by minus 50 minus the population mean, if we divide that by 10, which is a standard deviation in this case, we know that's going to be normal on 0, 1. That's how we standardize an arbitrary normal distribution. We subtract off the mean, then divide by the standard deviation. So if we do that, that's going to be a normal distribution for all I from 1 to 16. And also, since we have a random sample, if we add each of those together and square them, we'll have a sum of independent chi-squared random variables, all with 1 degree of freedom. So when we sum that up, we get a chi-squared random variable on 16 degrees of freedom. So in this case, we started with this probability. This is what we were asked to compute. The first thing we need to do is get that 10 on the inside. Well, to get the 10 on the inside, I really need to divide everything by 100. So we get 7.962 here when we divide that by 100, 26.3 on the right-hand side here when we divide that by 100. 100 is 10 squared, which is why we can pull the 10 on the inside and leave the squared on the outside. All right, so this inside part is chi-squared on 16 degrees of freedom, so we need to go to the chi-squared table and look up in the 16 degrees of freedom row. We need to find these numbers, the 7.962 and the 26.3, and find out what probabilities those correspond to, so that we can then subtract those probabilities to get the answer that we want. For the 26.3, we find out the probability that the chi-squared on 16 degrees of freedom is less than that particular value is 0.95. Similarly, if we look at the 7.962, we get the probability is 0.05 that the chi-squared random variable is less than that. So we get 0.9 for the probability. For part B, we attack it in a similar way, except that we need to remember that when we do the x bar minus x bar squared, add those up and divide by n minus 1, we get the sample variance. Then if we take n minus 1 s squared over sigma squared, we get a chi-squared of n minus 1 degrees of freedom. So in this case, if we pull a 10, which is the standard deviation on the inside, we know that this is going to be chi-squared of 15, because notice that this is sigma squared, that's 100 that we've divided by, and when we have n minus 1 out in front, it of course cancels out the 1 over n minus 1 here. So in this case, this random variable is going to have 15 degrees of freedom for the chi-squared random variable, rather than the 16 it was in the previous part. So just like we're going to attack this just like we did the last part, divide everything by 100, pull the 100 as 10 squared, pull the 10 on the inside, get these two numbers now, the 7.261 and the 25, break it up as two separate probabilities so that we can look up in the 15 degrees of freedom row now in the chi-squared table, the numbers 25 and 7.261. Notice in for those particular values, again, they're going to correspond to probabilities of 0.95 and 0.05, so we get a probability of 0.9.